Welcome to the Deep Dive. We're here to take information you're curious about and, well, make it clearer.
Make it make sense.
Exactly. And today we're digging into critical thinking skills and advanced problem-solving strategies for Cambridge AS&A Level Physics 9702, the 2025 syllabus version, by Dr. Bangbos. Think of this as your fast track to getting the really key stuff without getting bogged down in all the details.
Right. And our goal really is to see how this document helps you build up those crucial critical thinking muscles, and the problem-solving techniques for physics.
Yeah, moving past just like knowing the formulas.
Exactly, to really getting the ideas and being able to use them effectively.
Spot on. And what I like about this source is how it's laid out. It goes topic by topic through the AS syllabus.
Yeah, it's very structured.
And for each one, it points out, okay, here's how to think critically, here are some solid problem-solving approaches, and even how you can become more confident and self-reliant in that specific area.
It's a great roadmap.
Okay, so let's jump in. First stop, physical quantities and units, right at the start.
Well, what's really interesting here is that critical thinking is baked in from the very beginning. It's not just, learn this unit. It's about building that kind of physicist's gut feeling, being able to estimate, to look at a number and think, does that actually make sense in the real world?
Like a reality check.
Pretty much. It helps you flag answers that are just way off, which saves time, obviously, but also points to maybe a deeper misunderstanding.
I like that. Physics intuition.
Yeah.
Yeah.
And then there's the focus on unit consistency and error propagation. It highlights how seemingly tiny errors or uncertainties can actually snowball.
Right. They can add up and really affect the final answer.
They absolutely can.
So it's more than just getting the number. It's understanding its plausibility and reliability. And for problem solving, the document talks about dimensional analysis.
Oh, yeah, that's a big one. Using dimensions, the fundamental units like mass, length, time, to check if your equations are even physically consistent.
So making sure the units match on both sides of the equal sign.
Basically, yes. If they don't, you know you've made a mistake somewhere in your derivation or setup. It's a powerful self-checking tool.
Okay. And it also mentions different types of errors.
Right. Systematic versus random errors. Understanding that difference, whether your errors are consistent flaws in the setup or just unpredictable fluctuations, is key to evaluating how trustworthy your experimental results actually are.
Got it. So really foundational stuff for careful work.
Definitely. It's
Yeah.
about building a really solid, thoughtful approach right from the start. And the self-reliance part, encouraging you to make your own personal guide for units and errors, and really drilling those SI units and prefixes. That's all about building a reliable foundation you can always fall back on.
Makes sense. Okay, moving on to kinematics, how things move. The critical thinking here seems very visual. Lots about graphs, right?
Absolutely. It's
Right.
pushing you beyond just plotting points or reading values off a graph.
So what's the deeper story the graphs tell?
Well, that's the question, isn't it? What's hidden in that visual? The document guides you to look for the trends, the patterns, but also the anomalies, the bits that don't quite fit.
Okay.
Think about the gradient, the slope, of a displacement time graph. That's not just a number, it is the velocity.
Right.
And the area under a velocity time graph, that gives you the displacement. So these mathematical features have direct physical meaning.
The graph is like a visual language for motion.
Cool. And for solving problems in kinematics.
A key strategy highlighted is breaking down complex motion into simpler stages, which honestly is a good tactic for lots of problems, not just physics.
Yeah, that seems widely applicable.
And there's a crucial warning. Only use those standard equations of motion, the SUV equations when acceleration is constant.
Ah, that's a classic pitfall, isn't it? Easy to forget that condition.
Very easy. Understanding when a tool applies is just as important as knowing how to use it.
Good point. And the self-reliance aspect.
Yeah.
Sketching your own diagrams. Yes. Sketching motion diagrams, drawing the graphs yourself, even trying to predict roughly how something will move before you calculate it, that builds a much more intuitive understanding, visual thinking.
Connecting the math to what you'd actually see. Okay, next up, dynamics. The why behind motion forces.
Right. And the critical thinking challenge here is often dealing with multiple forces acting at once.
Yeah.
It's rarely just one simple push or pull in reality.
Things get complex fast. So how does the document suggest we approach that?
Well, it encourages applying Newton's laws in situations that might be a bit unusual, not just the standard textbook examples, like thinking about forces on something inside a moving elevator.
Ah, so it tests your conceptual grasp, not just formula application.
Exactly. Are you just plugging numbers, or do you really understand the principles? And for problem solving, the free body diagram, the FBD, is presented as absolutely essential.
I remember those. Drawing all the force arrows on an object.
Yeah, they're incredibly powerful visual tools. They help you isolate the object and see all the forces acting on it clearly. Makes tackling complex force situations much more manageable.
Like organizing the chaos.
Pretty much. And the document also stresses using vector analysis properly, because forces and acceleration have direction, not just magnitude. You can't just add them like simple numbers.
Crucial detail. Direction matters. And building confidence.
Comes from tackling those trickier, maybe non-routine problems, like figuring out the tension in ropes holding something up at an angle.
Yeah, those can be tough.
But also, and this is important, justifying each step in your solution by referencing the underlying physical laws, Newton's first, second, or third law. That reinforces the fundamentals.
So it's about logical progression grounded in principles. Got it.
Okay, let's look at forces, density, and pressure. Here, critical thinking starts with understanding equilibrium, that state of balance conceptually, before jumping into the math.
Visualizing the forces balancing out. Yeah, that seems smart.
And thinking about stability through the lens of the center of gravity. Why do some things stand firm while others topple easily? It connects to real-world observations.
Like designing a stable chair or understanding why a racing car is built so low.
Exactly. Practical applications. And for problem solving, the idea of using moments, or torques, for rotational equilibrium comes in, dealing with turning forces.
Right, not just forces causing straight-line motion.
And understanding buoyancy not just as things float, but calculating the buoyant force from the pressure difference in the fluid that provides a much deeper explanation.
Ah, so it's the pressure pushing up from underneath that's greater than the pressure pushing down from above.
Precisely. And for self-reliance, things like building simple physical models, like a lever balance, can really help solidify understanding, hands-on learning.
Or connecting fluid ideas to things like how submarines work or hydraulic lifts.
Yeah, making those connections to tangible, real-world tech makes abstract concepts stick.
Definitely. Okay, work, energy, and power. The critical thinking angle here seems to be about facing reality.
Yes. Moving beyond the ideal, frictionless world of introductory problems.
So considering energy losses, friction, air resistance, heat, all that messy stuff.
Exactly. Recognizing that in real systems, energy is almost always lost, transformed into less useful forms like heat, and then thinking critically about efficiency.
How much useful work do you get out compared to the energy you put in?
Right. And how could you potentially improve that efficiency? That's starting to think like an engineer.
Okay. And problem-solving strategies here.
Combining the concepts. Using energy principles alongside motion equations. They aren't separate worlds, they're deeply interconnected.
Using conservation of energy perhaps to find a speed, then kinematics to find time.
For example, yeah. And also seeing how you can derive expressions for power from different starting points, either work done over time or force times velocity, gives you flexibility.
Different tools for different situations, and building confidence.
Comes partly from tackling problems presented in non-standard ways, like maybe you're given a velocity time graph and has to find the power. You have to adapt your skills.
Not just plugging into a formula you memorized.
Exactly. And also, consciously reflecting on energy conservation in everyday things. Thinking about the energy transfers happening in a bouncing ball, or, like the source mentions, an escalator. Makes it less abstract.
Seeing the physics in action, good stuff. Okay, let's tackle waves and superposition together.
Sounds good. For critical thinking with waves, visualization is huge, since you can't usually see waves like light or sound directly.
Right.
Using simulations, analogies like water ripples, helps make their behavior more concrete, more intuitive.
Making the invisible visible.
Yeah. And understanding how a wave's energy connects to its amplitude and intensity. That's fundamental to how waves transmit energy, which is, a primary function.
It's not just about the wiggles, it's about the energy they carry.
Spot on. And then digging into why interference patterns happen, needing coherent sources, waves overlapping in specific ways.
Like with Young's double slits.
Exactly. Or why diffraction, that bending of waves around corners or through gaps, only really becomes noticeable when the gap size is similar to the wavelength. It's about the conditions.
Understanding the why behind the phenomena. And for problem solving.
Well, applying the basic wave equation, VO is key across all sorts of waves, but also practical skills like interpreting oscilloscope displays accurately.
That seems very lab-focused.
It is. And being able to logically apply the formulas for interference patterns, like the double slit formula or the diffraction grating equation, and drawing clear diagrams of stationary waves showing nodes and antinodes.
Visualizing those standing waves and self-reliance.
Using digital tools and simulations again is great here. Trying to reason through interference problems like figuring out if a point will be bright or dark before just plugging into XAD. That builds deeper conceptual understanding.
Getting the feel for it first.
Yeah. And predicting how waves might behave if they entered a new medium, or evaluating real-world examples of the Doppler effect, like ambulance sirens, connecting theory to observation.
Makes sense. Okay, let's group electricity and DC circuits together too.
Right. Critical thinking here often involves bridging scales, connecting the microscopic movement of individual charge carriers, electrons usually,
The tiny things we can't see.
to the macroscopic current that we can actually measure in a circuit. That's a big conceptual leap.
From the unseen to the measurable.
Exactly. And questioning how factors like temperature affect a material's resistivity, understanding that resistance isn't always fixed.
Like in a light bulb filament getting hot.
Perfect example. Also, critically evaluating why real batteries or power supplies have internal resistance, which means they can't deliver unlimited current, and some energy is lost internally.
Practical limitations again.
Yep. And really grasping the implications of Kirchhoff's laws, his current law, conservation of charge at a junction, and voltage law, conservation of energy around a loop. Those are the absolute bedrock of circuit analysis.
The fundamental rules of the road for circuits.
Couldn't have said it better. For problem solving, it's about integrating all those fundamental equations, QIT, VIR, PVI, and so on,
Using them together.
and being able to sketch and interpret IV characteristic graphs, especially for non-ohmic components where resistance changes. That visual understanding is key.
Like diodes or thermistors.
Right. Tackling multi-loop circuits often requires setting up and solving simultaneous equations. Using Kirchhoff's laws, they can be challenging, but it's powerful for complex systems.
Definitely a step up in complexity.
And analyzing how potential dividers behave when you change the resistances, understanding how you can use them to get variable voltage outputs. That's circuit control.
Okay. And building confidence in electricity.
Getting your hands dirty. Designing, building, and testing simple circuits. There's nothing like seeing it actually work, or figuring out why it doesn't.
Troubleshooting skills.
Exactly. Analyzing circuit behavior under fault conditions, building models of more complex setups, it all makes the theory much more tangible and useful. Debugging based on your understanding.
Practical application reinforcing the theory. Great. Last topic area. Particle physics.
The really fundamental stuff. Critical thinking here is often about the process of science itself. How does experimental evidence, like from particle scattering experiments,
Firing particles at targets and seeing how they bounce off.
how does that evidence actually shape and constrain our theories about what matter is made of at the most basic level? Quarks, leptons.
It's about the interplay between experiment and theory.
Absolutely. And questioning the role and implications of the fundamental conservation laws, energy, momentum, charge, but also things like baryon number, lepton number, down at this subatomic scale. They're still the guiding principles.
Rules still apply, even down there. Problem solving.
Often involves using the quark model to explain why certain particles exist or how they decay into others. Understanding the quark composition helps make sense of the particle zoo.
Like figuring out the recipe for a proton or neutron.
Sort of, yeah. And applying decay equations rigorously, making sure all those conserved quantities, nucleon number, proton number, charge, etc., balance on both sides of the reaction. It's like meticulous accounting.
Keeping track of everything.
Yeah.
And self-confidence in this rather abstract area.
Comes from being able to reconstruct decay pathways yourself, using those fundamental principles, applying your knowledge to predict what might happen in hypothetical particle reactions you haven't seen before.
Pushing the boundaries of what you know based on the rules.
Exactly. Kind of like solving nature's puzzles.
Okay, so we've covered the topics. Now the document wraps up with some broader techniques for integration, for lifelong learning.
Yeah, these are really valuable takeaways that go way beyond just physics, I think.
Yeah.
The first is what it calls Socratic self-questioning.
Asking yourself questions.
Constantly asking why and what if as you solve problems. Don't just find the answer. Probe deeper. Why is this the method? What assumptions are being made? What if I change this condition?
So instead of just calculating a result, you ask, How does this relate to impulse? Or what if friction were higher?
Precisely. It forces deeper engagement. Then there's error analysis.
We touched on errors earlier.
Yes, but this is broader. It's not just noting you got an answer wrong, but actively investigating how the error happened. Was
Yeah.
it a calculation slip, a conceptual misunderstanding, a misread problem?
Finding the root cause.
Exactly, because that's how you actually learn and avoid repeating it. Think about an experiment. Was the error due to measurement limits or a flawed assumption in your model?
Got it. Diagnose the mistake, don't just correct it.
Then linking physics to real-life applications. We've mentioned this, but the document really stresses it. Actively looking for physics principles in action around you.
How does my microwave work? Why does a curveball curve?
Right. It makes abstract ideas concrete, memorable, and relevant. Next is interleaving practice.
Interleaving, mixing things up.
Yeah. Instead of drilling one topic into the ground before moving on, that's called blocking, mix problems from different topics together during your study sessions.
So don't just do kinematics problems for an hour, then dynamics for an hour.
Maybe mix some kinematics, dynamics, and energy problems together.
Okay.
It feels harder initially, but research shows it leads to much better long-term retention and ability to choose the right approach when faced with an unknown problem. It builds flexibility.
Interesting. Prevents just memorizing procedures for one topic at a time.
Exactly. And the final technique is peer teaching.
Explaining it to someone else.
Yes. Trying to articulate a concept clearly enough for another person to understand is one of the most powerful ways to solidify it in your own mind. It forces you to organize your thoughts and expose any gaps in your own understanding.
The if you can't explain it simply idea.
Pretty much. So, pulling all this together, what this document lays out so well is that mastering these skills, the critical thinking, the problem-solving strategies, isn't just about acing a physics exam.
Right. It's bigger than that.
It really is. You're equipping yourself with a way of thinking, a way of approaching complex information and challenges that's valuable for life, really, in any field.
Building a toolkit for scientific inquiry and just confident thinking.
Yeah, confident engagement with complexity.
So here's a final thought for you, the listener, to chew on. Consider how these strategies we've talked about, breaking things down, asking why, looking for fundamental principles, analyzing errors, connecting ideas to reality. How could you apply that kind of analytical approach to other parts of your life?
Beyond physics.
Yeah. Maybe to decisions you have to make, or challenges in your work or studies, whatever your field is. What new perspectives or solutions might open up if you looked at things through that kind of critical problem-solving lens?
Something to think about.
Definitely. We hope this deep dive has given you some useful insights. Keep exploring, keep questioning. Thanks for joining us.